はどこにありますか？これです。これです。これ。じゃあこれと一緒に。ロンドセラーで外して剥がせる。これ剥がせる。これは別釣りなので、参考して。ゆきさんのここにあるから、
林。
じゃあ、次は、じゃあお願いします。
Good morning, everyone. Thanks for coming here for my presentation. My name is Udara Manawadu. My doctoral thesis is on an adaptive multimodal interface for collaborative control of human-centered automated vehicles. So first, let me give an abstract of my doctoral thesis. So the research questions I address in my thesis are the lack of driver control, low flexibility, and low adaptability of automated vehicles, and also out-of-the-loop performance of humans, also a major problem in automated vehicles when dealing with humans. So I adopted a methodology by proposing a collaborative control method to control lateral and longitudinal motions of automated vehicles. And to facilitate collaborative control, I developed a multimodal human-machine interface system and evaluated it through a series of experiments. And among my key findings are that I found that there is a need for collaborative control, tactical level input method, because we found that 70% of the drivers, they use this method compared to manual driving and automated driving. And the proposed multimodal human-machine interface, it significantly reduced driver workload, minimized input errors, and improved the efficiency of interaction. And the significance of my findings are that the tactical level input with collaborative control can be used in short-term system limitations for takeover situations. And as an application, the collaborative control method, along with my HMI, can be applied into teleoperation of automated vehicles. So this is the outline of my presentation today. First, I will introduce the advantages and disadvantages of automated vehicles, and then I propose my collaborative control method, along with the development of the driving simulator. And then I introduced the multimodal human-machine interface, and followed by a series of experiments I conducted to evaluate the HMI. So yeah, let's take a look at automated driving. So it's a very hot topic currently. Every country and automakers, they are racing towards having automated vehicles by 2020 or soon. So there are a lot of advantages behind automated driving. So first of all, we can see improved safety because sensors and computation systems can take decisions much quicker than human mind. And also it can improve driver and user comfort, also increasing mobility and accessibility to a lot of people. And also it can reduce energy use and emissions. But it can come with several drawbacks as well. So if you look at the picture on the bottom, this is a prototype of automated vehicle made by General Motors earlier this year. So you can see there are no vehicle control interfaces there. So as you can imagine, as disadvantages, lack of driving pressure or lack of driver control is one of the major drawbacks in automated vehicles. And arising from that, low adaptability to system limitations is also another key problem. And also when they encounter system limitations, they need input from the human driver. But out-of-the-loop performance of humans with automation is also a disadvantage or a challenge when dealing with automated vehicles. So let me give a brief introduction to different levels of automation. So SAE has introduced 6 levels to make it easy to describe different levels, the functionalities. So level 0 is basically no automation. So driver conducts the driving task entirely, manually. And level 5 being full automation with no driver. So it's like unconditional full automation, which is very far into the future. But currently we have level 2, level 3, level 4 systems. Level 2 systems, we have them commercialized on the road, like Nissan ProPilot or Tesla Autopilot. But level 3 and level 4 still in development. But the main feature of level 2, 3, 4 is that there is the human driver conducting the driving task, sometimes engaging partially and taking control fully in certain situations. So there are specific set of problems that we need to address in human-centered automated vehicles. So if you look at the main components of typical automated vehicle, you can see localization, perception, planning, and control. They are very widely researched areas. But HMI, human-machine interface interaction for automated vehicles, is relatively a new topic. So it's a novel research area when it comes to automated driving. So I identify there are three aspects in HMI, which is internal HMI that deals with passengers and user or driver of the vehicle, and external HMI that deals with external road users like pedestrians, cyclists, or other road users. So HMI is the main interface that connects the automated driving system with the driver, the road users, and ultimately the society. So this is, although this is relatively new, but it's a very important research area. So this slide summarizes my objectives and contribution for my thesis. So as I mentioned before, lack of driver control and authority of control is a major drawback. We found that from our own experiments. And also recently, there was a study conducted in the US with 1,000 respondents that 72% of them mentioned that lack of driver control is one of their major concerns when if they decide buying an automated vehicle. So as a solution, I propose and introduce a tactical level input method for collaborative control of automated vehicles. And also among the drawbacks are the increasing degree of automation. It reduces the situation awareness in human-machine systems. This is not relevant only for automated vehicles, but in any human automation interaction, it's common. So as a solution for that as well, I propose to develop a multimodal human-machine interface to enable bilateral control to enhance situation awareness of the drivers. So moving on to collaborative control. So what is collaborative control? Let's say if we take the human-centered automated vehicle, there are two agents. The automated driving system, which consists of the sensors and actuators and the control algorithms, and the human component. We also have a sense, plan, act loop and our own superior human intelligence. So both these actors, agents, can act on the environment. So what my contribution is, I created this new HMI, which uses distributed intelligence theory and distributed situation awareness theory to overcome the limitations in driver situation awareness using machine intelligence, and to overcome the limitations in machine intelligence and driving policy using human intelligence. So still on theory, so this is quite a popular metaphor when it comes to automation human interaction. So this is called the horse metaphor or H metaphor. So a rider of a horse usually controls or commands the horse using voice or haptic, like using the rein or using their legs. It's like a multimodal interaction. And most importantly, the horse has its own intelligence. Human has its own intelligence. And it's kind of an automation human system dating back to ancient history. So getting inspiration from this, recently, the new horse metaphor for automated driving is coming up. So this highlights my contribution in this area. So here we have on x-axis the driver engagement, on y-axis the automated driving system engagement. So if the traditional systems is like this, so if the AD system engagement is 100%, the driver engagement is very low. But we want to have the driver control as well as automation control in this area. So it creates the excitement of control and also the safety and reliability of automation control. So that's the basic philosophy behind my research. So yeah, and one more thing. So this highlights the different levels of driving task. So it has 3 levels. One called the strategical level, which means planning of the trip. It can take days or minutes before we start the trip. And tactical level means, for example, strategical level can be making the decision on the destination. And tactical level is like lane change, overtaking, that can take 5 to 60 seconds to decide and execute. And finally, operational level, where we control the driving task in real time, speed and directional control. So we adopted this Micon's theory on different levels of driving automation, driving task, to collaborative control in automated driving. So if you look at automated vehicle, we can use strategical level to input the destination. So we can use the voice or touchscreen command to input the destination. And for operation level control, you can move back to manual driving and use the steering wheel and pedals. But how can we input tactical level commands? So there's a need for a new type of interface. So, and we identified that tactical level input has the advantages of flexibility of control, as in operational level, and safety and comfort of fully automation driving. So actually, related works are relatively very low in this area because it's still starting to build up. So, but we found quite similar work to ours conducted in Sweden, involved with Volvo. So to summarize, they showed that they also used a tactical level control method for highly automated vehicles, and they showed that driver accepted tactical commands. They used the touchscreen interface and gear stick interface. But the limitations we found in their research is that they did not investigate any multimodal or bidirectional control interfaces. And also they did experiments like Wizard of Oz style. So there's a human controlling, acting as the automation. So we found that those are the limitations we need to address in our research as well. So first step of our methodology. My methodology is that we need to develop a driving simulator which is capable of automated driving, and then develop a multimodal human-machine interface for tactical level input, and then evaluating it through experiments. Okay, so this is a very important slide in my presentation. So this highlights what are the tactical level input commands. So for collaborative control, we used a tactical level input method, and we used 3 types of control inputs: longitudinal control, lateral control, and location-specific control. Longitudinal control means speed controlling, acceleration, deceleration, stopping, go, likewise. Lateral control means lane changing, overtaking, merging, turning, and so on. And location-specific control means like selecting a parking spot. The bottom line is I proposed a set of lateral and longitudinal control commands for tactical level input. And then we developed a driving simulator which is capable of evaluating our system and capable of fully automation. So we implemented automated driving in highway, and so that's capable of lane changing, merging, and also automated driving in urban area, so that can detect traffic lights and other vehicles, interact with other vehicles, turning and overtaking as well, and also it has the capability of automated parking. So this driving simulator has the functionality to reproduce real-world events and interactions, and to efficiently evaluate driver behavior and interaction with automation. And also we can use this to train drivers on using automated vehicles in different levels of automation. So we developed this simulator which is capable of evaluating our control method and the interface. So moving on, from this slide onwards I will introduce my HMI system. So first I thought to introduce why we chose a multimodal system. So from previous research we identified that compared to unimodal interfaces, multimodal interfaces have the functional advantages, like improved recognition and understanding, faster and intuitive interaction, and also the ability to adapt to different environment and users. So we came up with 3 modalities, basically: haptic, hand gesture, and touchscreen. And this interface system can have multimodal input and multimodal feedback as well, using visual, audio, and haptic modalities. So the main purpose of these HMIs are to enable command level driving, collaborative driving through tactical level input, and to enable situation adaptive interaction with the automation and human driver, and to facilitate intent communication in real time, and to support and enhance the situation awareness. So from this slide onwards, I will introduce each of the interface modalities. So we use the hand gesture in HMI. So the sensor we use is the leap motion sensor. So it has the gesture interaction space like an inverted 3D pyramid. So we placed it just behind the steering wheel to avoid any unintentional inputs. So hand gestures, in human communication, we use hand gestures a lot. So it's human-like interaction and also intuitive. So we defined several hand gesture types to map with the tactical level inputs that I introduced before. So we have a horizontal swipe, a vertical swipe, and circle gestures. So to input tactical level commands. And this is my gesture classification framework. So basically it's like this. So the sensor detects the hand in 3D space and checks if it is a valid gesture that we defined in previous slide, and then classify it into whether it's acceptable or not